So today we're going to be doing questions on redox and moles. The first question that we have says ammonium nitrate NH4NO3 decomposes into N2O and H2O on heating. Which statements are correct? The ammonium ion is behaving as a reducing agent. The nitrate 5 ion is behaving as an oxidizing agent. It is a redox reaction. It is a disproportionation reaction. Now over here we have the following reaction. We have ammonium nitrate decomposing to form N2O, that's nitrous oxide, okay, or nitrogen 1 oxide, and we have H2O. Now if you were to balance this equation, you just have to balance the hydrogen, so that would be 2H2O, right? So now we have 2 nitrogens on both sides, we have 3 oxygens on both sides, and we have 4 hydrogens on both sides. So now over here, right, we first have to look at the oxidation numbers. So if you think about the ammonium ion, right, you have NH4 plus, right, and we know hydrogen is going to be plus 1, and we have 4 hydrogen atoms, so that's 4 times plus 1. We have 1 nitrogen atom, let's call that X, and the overall oxidation number is plus 1 because that's the charge on the ion. So we get the oxidation number of nitrogen as negative 3, right? We get plus 1 minus 4. And then in the nitrate ion, right, that's NO3 minus, and that's NO3 minus over here. We know that the oxidation number of nitrogen is plus 5, right? We have 3 oxygens, which are minus 2. We have the overall charge, that's the overall oxidation number, that's minus 1. Then X is plus 5, and that's also mentioned in the question. We have the nitrate 5 ion, right? And then lastly, if you look at the product, here, right, we have 2 nitrogens here. We have an oxygen, which is minus 2, and the overall oxidation number is 0 because it's a neutral compound, and we get X is equal to plus 1. So now, if you look at the first statement, the ammonium ion is behaving as a reducing agent. That is true because a reducing agent undergoes oxidation. So that means that it's being oxidized. And we can clearly see that the oxidation number of the nitrogen is increasing from minus 3 in the ammonium ion, to plus 1 in the product. The second statement says the nitrate 5 ion is behaving as an oxidizing agent. That means that it's being reduced, and that's also a true statement. We can see that the nitrogen is going from plus 5 in the nitrate ion to again positive 1 in N2O. That's nitrous oxide or nitrogen 1 oxide, right? So we can see that the oxidation number is decreasing. So the nitrogen is being reduced. So the nitrate ion is being reduced. So therefore, it is the oxidizing agent. So statements 1 and 2 are true. Now statement 3 is obviously true because it is a redox reaction. Now statement 4 is not true. It is not a disproportionation reaction. Now you might say, well, a disproportionation reaction, a single species is both simultaneously oxidized and reduced, right? But this is not a single species. In this compound, we have the ammonium ion and the nitrate ion. We have the ammonium ion and the nitrate ion. They're two separate species in this compound. The ammonium ion is undergoing oxidation. It's the reducing agent, right? The nitrogen is going from minus 3 to plus 1. Oxidation number is increasing. And the nitrate ion is undergoing reduction. Nitrogen is going from plus 5 to plus 1. It's undergoing reduction. So therefore, it is the oxidizing agent. And they're two separate species, the ammonium and the nitrate ion, that are reacting with each other in a redox reaction. So it is a redox reaction, but it is not a disproportionation reaction. Another way to think about this is when you talk about disproportionation, you're going from a single oxidation number to 2 different oxidation numbers. You're going from one single oxidation number to 2 different oxidation numbers. In this case, if you look at the reactant, you already have 2 different oxidation numbers to begin with. One of them is being reduced, one of them is being oxidized. To give you an example of a disproportionation reaction, right, this would be a disproportionation reaction. So for example, if you think about the reaction of NO2 with H2O, right, you get HNO3 plus NO, right, and the balanced equation for this is you have 2HNO3 here and you have 3NO2 over here. Now over here, you're going from a single oxidation number on the left hand side. Nitrogen is plus 4 here, right? Nitrogen is plus 4 here, and some of the nitrogen atoms are going from plus 4 to plus 5. In nitric acid, the nitrogen has an oxidation number of plus 5. So you're going from plus 4 to plus 5, and some of the nitrogen atoms are going from plus 4 to plus 2. This is a disproportionation reaction. This is a disproportionation reaction because you're starting with a single species that has a single oxidation number for this nitrogen, and some of the nitrogen atoms are being oxidized to plus 5 and some of them are being reduced to plus 2. This is not a disproportionation reaction because you have the ammonium and the nitrate ions where the nitrogens have different oxidation numbers. So one of them is the reducing agent, that would be the ammonium ion, and one of them is the oxidizing agent, that would be the nitrate 5 ion. So the answer over here is B. NCl3 reacts with H2O. The oxidation state of nitrogen does not change in this reaction. Which statement is correct? Now over here, right, since the oxidation number of nitrogen is not changing in this reaction, it's easy for us to figure out the oxidation number of nitrogen in ammonia. Now if you think about ammonia, right, we have nitrogen, let's call it X, right, we have 3 hydrogens which are +1, right, because hydrogen is bonded to a non-metal here, and the overall oxidation number is 0, so we get X is equal to -3. So that means that the oxidation number of nitrogen here is -3, and that would also mean that the oxidation number of nitrogen in NCl3 is -3 because it's not changing in this reaction. Now if nitrogen over here is -3 and it's -3 in the product, that means that the chlorine will be +1 just like hydrogen. So we have 3 chlorines over here, each of which is +1. So the oxidation number of chlorine over here is +1. Then if you look at hydrogen over here, it's +1 again. The oxygen here is -2. The hydrogen here is +1, right? Again, that's not changing. The hydrogen in HClO is also +1 because it's bonded to a non-metal. The oxygen is -2. Then you have +1 -2, that's -1. That means this chlorine over here must be +1. So chlorine is +1 on the left and +1 on the right. Hydrogen is +1 on both sides. Oxygen is -2 on both sides, and nitrogen is -3 on both sides. So there are no changes in oxidation number in this reaction, which means that this is not a redox reaction. Two half equations are shown. The equation for the reaction with manganate 7 ions and sulfite ions is shown. Which statements are correct? So we need to balance this equation first to figure out which statements are correct. Now in order to write the balanced equation, right, we have the two half equations. We have manganate 7 ions, right, they're undergoing reduction, right. So manganate 7 is the oxidizing agent. This is the half equation for reduction, and then this is the half equation for oxidation, right. Here the sulfite ions are undergoing oxidation to sulfate. Now if you had to write down the overall equation for this reaction, you need to balance the number of electrons. We have 3 electrons on the left here and 2 electrons on the right in the second half equation. So we're going to multiply the top equation by 2. I'm going to multiply the bottom equation by 3, right? If we do that, we balance the number of electrons. So if we do that, we get 2MnO4 minus reacts with 4H2O, 6 electrons, and we have 2MnO2, and we have 8OH minus. And then in the second equation, we multiply it by 3, the second half equation, so this becomes 6OH minus plus 3SO3 2 minus gives you 3SO4 2 minus plus 3H2O and then 6 electrons. So obviously if you add these two equations together, right, the electrons cancel out because you have 6 electrons now on the top and the bottom, right? And then what we have here is this. We have 2MnO4 minus, right? That's from the first half equation. If you add up the left hand side, we have 2MnO4 minus, right? Now on the left here we have 4H2O and on the right we have 3H2O, right? Here we have 4H2O and here we have 3H2O. So if you balance that out, we get 1H2O over here. We get 1H2O. Okay, then we have 6OH minus on the left and we have 8OH minus on the right over here. We have 6OH minus on the left, we have 8OH minus on the right. So if we add these together, if we're adding the left hand sides together, right, we get 6 on the left, 8 on the right. So there's a net 2 OH minuses on the right. So that becomes 2 OH minus. And then for sulfite, we have 3. And then we have 2 MnO2 and then we have 3 sulfate. So now if you look at the first statement, U is equal to X is equal to Z. U is 2, X is 2 and Z is 2. So the first statement is correct. Manganese is reduced to oxidation state +4. That is also correct because we have manganate 7 over here. So manganese has an oxidation number of +7. And then in MnO2, we have two oxygens which are -2 each. So that's 2 times -2, that's -4, which means that the manganese must be +4. So the manganese is going from +7 to +4. So the oxidation number is decreasing. So it is being reduced to an oxidation state of +4. So statement 2 is correct. And then statement 3 says sulfur is oxidized from oxidation state +4 to +6. So initially we had the sulfite ion, right? SO3 2 minus. You guys should know that over here sulfur is X. We have 3 oxygens which are -2 each. The overall is -2, so X is +4. And then if you talk about the sulfate ion, SO4 2 minus, let's say sulfur over here is Y. And then we have 4 oxygens which are each -2, and the overall oxidation number is -2 because that's the charge, and we get Y is equal to +6. So sulfur is going from +4 to +6. So it is being oxidized because the oxidation number is increasing from +4 to +6. So the answer is A. All three statements are correct. Zinc atoms can be oxidized to Zn2 plus ions by dichromate 6 ions in acid solution. Chromium is reduced to chromium 3 in this reaction, that's Cr3 plus. Which equation is correct? We're just going to try balancing this equation normally, right? We have dichromate 6, that's Cr2O72 minus, in acidic conditions reacting with zinc to form Cr3 plus, that's chromium 3, plus Zn2 plus. Zinc is being oxidized from the metal from 0 to +2, right, to form Zn2 plus, and we have H2O, right? Remember, whenever you have an 8 ion, whenever you have a polyatomic ion, an anion with oxygens, right, that H plus will take away those oxygens to make H2O. Now, if you think about the oxidation number of chromium, right, chromium is being reduced in this reaction, right? Dichromate 6 is your oxidizing agent. It's undergoing reduction. Specifically, it's the chromium that's being reduced from +6 to +3. And if you think about what's being oxidized, it's the zinc from 0 to +2, right? 0 in the elemental form to +2 in the products. So the change in oxidation number for chromium is -3, right? The oxidation number is decreasing by 3 from +6 to +3. And the change in oxidation number of zinc is +2, right? The oxidation number is increasing by 2. Now, since the increase and the decrease of oxidation numbers have to balance, we're going to need 2 chromium atoms for every 3 zinc atoms. We're going to need 2 chromium atoms for every 3 zinc atoms, right? Here we have Cr2, so that's 2 chromium atoms for every 3 zinc atoms. 2 chromium atoms for every 3 zinc atoms. Then we just balance the rest of the equation. We have 7 oxygens on the left. We're going to have 7 oxygens on the right. So that'll be 7H2O. And then we have 14 hydrogens on the right. We're going to have 14H plus on the left, which gives us the answer as C, right? We have 1 Cr2O7, 3 zincs, 14H plus, giving us 2 Cr3 plus 3 Zn2 plus 7H2O. Acidified potassium manganate 7 reacts with iron 2 ethane dioate. The reactions taking place are shown. How many moles of iron 2 ethane dioate react with 1 mole of potassium manganate 7? Now, if you look at the half equations, we can clearly see that manganate 7 is your oxidizing agent. And manganate 7 is your oxidizing agent, right? Because in the half equation, we can see that manganate 7 is undergoing reduction, right? So it's your oxidizing agent, and this is the half equation. This is the half equation for the reduction of manganate 7. So this is the half equation for the reduction in this reaction. Now, obviously, if manganate 7 is the oxidizing agent here, it means that it's oxidizing iron 2 ethane dioate, right? That'll be a reducing agent. That'll be a reducing agent here, right? And it's undergoing oxidation. And here we have the two half equations. Here we have the two half equations that are showing the oxidation of FeC2O4, that's iron 2 ethane dioate. Now here they've shown the oxidation of iron 2 separately and C2O4 2 minus, that's the ethane dioate ion separately. But we can think of this entire thing. We can think of this entire thing as FeC2O4, right? Because in our compound we have one Fe2 plus, and we also have a C2O4 2 minus, right? So if you combine these two half equations together, you get the half equation. You get the half equation for the oxidation. So this is the half equation for the reduction. And if you think about the half equation for the oxidation, right? If you think about the half equation for the oxidation, this is what we have. What we have is, we have Fe2 plus C2O4 2 minus, giving us Fe3 plus 2 CO2 plus 3 electrons. I just added these two equations together, right? That's your half equation for the oxidation, because you have Fe2 plus and C2O4 2 minus both being oxidized in FeC2O4, and we have one of each. So if we just add these two together, we have Fe2 plus C2O4 2 minus, giving us Fe3 plus 2 CO2 plus 3 electrons. So these are our two half equations. Now the question is saying how many moles of iron 2 ethane dioate react with 1 mole of potassium manganate 7. So first we need to find the molar ratio between manganate 7 and iron 2 ethane dioate. Right, now we have the half equations, and we know that in the overall equation we're not going to have any electrons, right? The electrons have to be balanced for a redox reaction, so the gain and loss of electrons has to be balanced. So we can multiply the equation on top by 3, right? So that this becomes 15 electrons. We multiply the equation on the bottom by 5, the half equation by 5. So then we have a loss of 15 electrons. So what we end up getting is the electrons end up balancing. If we multiply the top equation by 3, the reduction half equation by 3, and the oxidation half equation by 5. Now, what we have here is this. We have 3 moles of manganate 7. 3 moles of manganate 7 are reacting with 5 moles of FeC2O4, right? Because again, this half equation is multiplied by 3, so we have 3 moles of manganate 7, 3 moles of manganate 7 reacting with 5 moles of FeC2O4. 5 moles of FeC2O4, right? This will become 5 and 5 over here. And the question is saying, if I had 1 mole of manganate 7, what is the number of moles of FeC2O4 that would react? And if we just cross multiply, we get 3n is equal to 5, which gives us n is equal to 1.67. So the answer over here is B. Oxidation numbers should be used to answer this question. A redox reaction takes place between hydroxyl ammonium ions, that's NH3OH plus, and acidified iron 3 ions, that's Fe3 plus. The products are iron 2 ions, that's Fe2 plus, H plus ions, water, and a compound of nitrogen. The mole ratio of reacting hydroxyl ammonium ions to reacting iron 3 ions is 1:2. Which nitrogen containing compound could be formed in the reaction? Now, since the question is saying oxidation numbers should be used to answer this question, we're going to do that. Now, the question says that the mole ratio of reacting hydroxyl ammonium ions to reacting iron 3 ions is 1:2. We're going to first write out that information. Right, we have the hydroxyl ammonium ions. The formula is given to us, NH3OH plus, and we have iron 3 ions, and they're reacting in a 1:2 ratio. So for every 1 mole of this guy, NH3OH plus, we have 2 moles of Fe3 plus. Now we're also told that the products here are iron 2 ions, H plus ions, water, and a compound of nitrogen. And we want to figure out what nitrogen containing compound we have. Now, let's think about the changes in oxidation number. Right? So if you think about what's being oxidized and what's being reduced here, right? Now, since the reaction is between the hydroxyl ammonium ions and the iron 3 ions, now over here, right, the oxidation numbers of nitrogen and iron are changing. Okay, the oxidation numbers of nitrogen and iron are changing in this reaction. Oxygen is -2 throughout, right, in water as well as in this ion over here. Hydrogen has an oxidation number of +1 throughout, right? We have H plus here, we have acidic conditions here as well, so we have H plus here. In water also, hydrogen is +1. So hydrogen is +1 throughout, oxygen is -2 throughout. So that means that only the oxidation number of nitrogen and iron is changing. Now, if you think about what's being reduced here, we know that iron is being reduced, right? Because we're going from Fe3 plus to Fe2 plus. So as far as the reduction is concerned, right, we have iron, the oxidation number is going from +3 to +2. And as far as oxidation then is concerned, it must be the nitrogen atom, okay, that has an increase in oxidation number. It must be the nitrogen atom that has an increase in oxidation number, because there's a decrease in oxidation number for iron. So now the goal is to figure out what is the change in oxidation number for the nitrogen, and what is the initial oxidation number and the final oxidation number. Now to find the initial oxidation number of nitrogen, we can look at this guy over here, right? You can say nitrogen is X. We have 4 hydrogens, each of which is +1. 3 plus 1, we have 4 hydrogens, each of which is +1. We have 1 oxygen, that's -2, and the overall oxidation number is +1. The overall oxidation number is +1, right? That's the charge. Then we get X plus 4 minus 2, that's X plus 2 is equal to +1. So that comes out to X is equal to -1. So the nitrogen is going from -1, that's the initial oxidation number, to something over here. Now in the question they said that 1 mole of NH3OH plus is reacting with 2 moles of Fe3 plus. Now if you look at the changes in oxidation number, right, the oxidation number of iron is decreasing by 1, so it's a change of -1. And the question is saying we have 2 moles of Fe3 plus. We have 2 moles of Fe3 plus for every 1 mole of this. So that means that we have 2 moles of Fe3 plus. We have 2 moles of iron atoms for every 1 mole of nitrogen atoms. We have 2 moles of iron atoms for every 1 mole of nitrogen atoms. So if the overall decrease in oxidation number for iron is -2, because we have 2 iron atoms, right, going from +3 to +2, so that's -1 times 2. So the overall decrease is -2. The overall increase for that 1 nitrogen atom must be +2. The overall increase for that 1 nitrogen atom must be +2. So then what is the final oxidation number of the nitrogen? Since we have this 1 nitrogen atom, right, the oxidation number is increasing by +2, where we go from -1, an increase of +2 would mean -1 plus 2, so the final oxidation number would be +1. The final oxidation number of the nitrogen would be +1. So now we need to figure out which nitrogen containing compound has nitrogen with an oxidation number of +1, and the answer over here is B, okay, N2O. Because over here we have 1 oxygen, the oxygen is -2, so that means each of the 2 nitrogens must be +1 for the overall oxidation number to be 0. A solution of SN2 plus ions will reduce an acidified solution of manganate 7 ions, that's MnO4 minus, to Mn2 plus ions. The SN2 plus ions are oxidized to SN4 plus ions in this reaction. How many moles of Mn2 plus ions are formed when a solution containing 9.5 grams of tin 2 chloride, SnCl2, is added to an excess of acidified potassium manganate 7 solution? Now, since we've been given the mass of tin 2 chloride and we were given the MR, right, that's a hint that we should find the number of moles. So let's find the number of moles of tin 2 chloride. The number of moles of SnCl2. That's just the mass divided by the molar mass. The mass is 9.5 grams. The molar mass is 190. So we get 0.05 moles. 0.05 moles. And in tin 2 chloride, of course, we have SN2 plus, right? Tin 2. So that means that we have 0.05 moles of SN2 plus. Now the question is saying that SN2 plus ions will reduce an acidified solution of manganate 7 ions, right? And MnO4 minus, manganese is +7, right? So that's manganate 7 ions. And this SN2 plus will reduce the manganate 7 to Mn2 plus. So the oxidation number here of manganese is +2. And since the SN2 plus ions are reducing agents, they'll undergo oxidation. They'll undergo oxidation to SN4 plus. They'll undergo oxidation to SN4 plus. So over here, right, we need to figure out how many moles of Mn2 plus ions are formed when this tin 2 chloride reacts with acidified manganate 7. And we know the moles of tin 2 chloride that we have. So we're going to balance the changes in oxidation numbers. So if you think about what's being reduced, right? Manganate 7 is being reduced. It's the oxidizing agent. Specifically, it's the manganese that's going from +7 to +2. And if you think about what's being oxidized, it's the tin going from +2 to +4. The change in oxidation number, for the manganese is -5, and the change in oxidation number for the tin is +2. So then if we had to balance the changes in oxidation numbers, we can say that we would need 2 moles of manganese atoms. We would need 2 moles of manganese atoms for every 5 moles of tin atoms, right? We would need 2 moles of manganese atoms for every 5 moles of tin atoms, because again, each manganese atom has a change of -5. So if we have 2 of those, the overall decrease is -10, and each tin has a change of +2. If we have 5 of those, we have an increase of +10, right? So the increase and the decrease have to balance. So that means that for every 2 manganese atoms, we would have 5 tin atoms reacting, right, in this reaction. And since we've been told that we have 0.05 moles, we have 0.05 moles of tin, how many moles of manganese would we have? If we cross multiply, we get N is equal to 0.02 moles. We have 0.02 moles of manganese atoms, okay, that would undergo reduction. So therefore, we're going to get 0.02 moles of Mn2 plus ions. So the answer is B. The next question says, when K2MnO4 is dissolved in water, the following reaction occurs. What are the values of A and C in the balanced chemical equation? Now in this reaction, right, we have to balance this using changes in oxidation number again. And the oxidation numbers of oxygen and hydrogen aren't changing. Oxygen is -2 throughout and hydrogen is +1 throughout. Okay, so they're not changing. So it's only the manganese that's changing. So this is again is a disproportionation reaction. This is a disproportionation reaction because a single species is undergoing both oxidation and reduction simultaneously. And we need to figure out the oxidation numbers. So if you think about MnO4 2 minus, right here, let's say that the oxidation number of manganese is X. We have 4 oxygens, each of which is -2, and the overall oxidation number is the charge, that's -2. We get X is equal to +6. So the initial oxidation number of manganese is +6. And in the products, we have manganate 7, that's MnO4 minus. You should already know by now that the manganese over here is +7. And we have MnO2, that's manganese 4 oxide. We have 2 oxygens, each of which is -2. So that's 2 times -2 for the 2 oxygens. Each oxygen atom has an oxidation number of -2. That means that the manganese over here is +4. So if you think about the reduction, right, if you think about the reduction, or the manganese atoms being reduced, right, the manganese is going from +6 to +4. And if you think about the oxidation, the manganese is going from +6 to +7. So some of the manganese atoms are being oxidized from +6 to +7, and some of the manganese atoms are being reduced from +6 to +4. Now the change in oxidation number for the manganese being reduced is -2 from +6 to +4, decreasing by 2. And for the ones being oxidized, there's a change of +1, right, from +6 to +7, an increase of 1. So that means again, if the changes have to balance, we would need 2 manganese atoms. We would need 2 manganese atoms to be oxidized for every 1 that's being reduced. We would need 2 manganese atoms to be oxidized, right? These are the ones that are being oxidized. We would need 2 manganese atoms to be oxidized for every 1 that's being reduced. So that means C over here is 2 and D is 1. We have to find A and C over here. We already found C, that's 2. And since we have 1 manganese atom here and 2 manganese atoms here, we'll have a total of 3 on the left hand side. So A would be 3. So 3 manganese atoms, right? If you had a total of 3 manganese atoms, 2 of them would be oxidized to +7, and then 1 of them would be reduced to +4. So A is 3 and C is 2. So the answer is B. In an experiment, 50 cm cube of 0.1 mole per dm cube solution of a metallic salt reacted exactly with 25 cm cube of 0.1 mole per dm cube aqueous sodium sulfite. The half equation for the oxidation of sulfite is shown below. If the original oxidation number of the metal in the salt was plus 3, what would be the new oxidation number of the metal? Now in this question, right, they've mentioned that we have the oxidation of sulfite taking place. We have the oxidation of sulfite taking place. That means that sulfite is the reducing agent, it's undergoing oxidation, and that means that because it's the reducing agent, the metal is being reduced. Okay, the metallic salt is being reduced. It's the oxidizing agent, right? It's oxidizing the sulfite. Now if it's being reduced and its initial oxidation number is plus 3, that's the initial oxidation number, and it's being reduced, that means that the final oxidation number has to be plus 2 or plus 1. It cannot be C or D. So we can eliminate those options. Because the metallic salt is being reduced, the oxidation number must be decreasing. Okay, now we're going to say that our metal ion over here is X. Okay, let's just say X is our metal ion, and we know that it's being reduced, right? And it's being reduced from plus 3 to some final oxidation number. We don't know, right? And if you think about what's being oxidized, right, it's the sulfur, right? The sulfur in sulfite is plus 4. You guys should be able to calculate these. You should know these. And the sulfur in sulfate is plus 6, right? This is sulfite or the sulfate 4 ion, and this is sulfate or the sulfate 6 ion. So the oxidation number of sulfur is going from plus 4 to plus 6. And we know that there's an increase of 2. We know that there's an increase of 2 because there's a loss of 2 electrons. It's being oxidized by 2 or by plus 2. So this is a change of plus 2. Now the question has also given us the initial concentrations and volumes of the metallic salt and the sodium sulfite. So we can say the initial number of moles of X, that's our metal for the metallic salt. Here it's a key assumption that we're making is that the metallic salt just has this 1 mole of X. So if we add 1 mole of salt, we would just have 1 mole of this metal ion X. Okay, that's an assumption here. Number of moles of X is the concentration times the volume. That is, concentration is 0.1 mole per dm cube and the volume is 50 over 1000. So we get 0.005 moles. And the number of moles of sulfite is also concentration times volume. Concentration is 0.1, volume is 25 over 1000. So we get 0.0025 moles. So we can say that for 0.005 moles of X is reacting with 0.0025 moles of sulfite. So then if you simplify this ratio, we get the ratio as 2:1. So what we're saying here is that 1 mole of sulfite is reacting with 2 moles of X. 1 mole of sulfite is reacting with 2 moles of X. So that means that for every 1 mole of sulfur atoms that are being oxidized, 2 moles of X are being reduced. 2 moles of X are being reduced. Now, if 1 mole of sulfite is oxidized, or 1 mole of sulfur atom is oxidized, the overall change in oxidation number is plus 2. So then we know that the overall change in oxidation number for X must be minus 2. Since the overall increase is plus 2, the changes in oxidation number have to balance. The overall increase is plus 2, the overall decrease has to be minus 2. And since we have 2 moles of X, the overall decrease is minus 2. That means each atom of X has a change in oxidation number of minus 1. It's decreasing by 1. Right, now the overall change is balanced. 1 mole of sulfur increases by 2. 2 moles of X decreased by 1 each. Right, so then we have a decrease of minus 2. So if the oxidation number of X is changing by minus 1, what's the final oxidation number? We have 2 moles of X, but each mole of X or each atom of X has a change in oxidation number of minus 1. So the final oxidation number must be plus 2. Okay. So that means that when 2 moles of X, right, change by minus 1, So that would be 2 times minus 1, that would be an overall decrease of minus 2, and then 1 mole of sulfur changes by plus 2. So the answer is B, right? Each X is changing by minus 1, but we need 2 of those to balance the changes in oxidation numbers. In aqueous solution, the acid HIO disproportionates according to the following equation, where M, N, P, and Q are simple whole numbers in their lowest ratios. The equation can be balanced using oxidation numbers. What are the values for N and P? Now they've mentioned in the question that we have a disproportionation reaction, and HIO is disproportionating. Specifically, it's the oxidation number of iodine that's changing, because hydrogen is plus 1 throughout and oxygen remains minus 2 throughout. So in HIO, the oxidation number of iodine can be found, right, as follows. We have hydrogen, which is plus 1, we have iodine, which is X, and we have oxygen, which is minus 2, and the overall is 0. So we get X is equal to plus 1. So the initial oxidation number of iodine is plus 1. The initial oxidation number of iodine is plus 1. In the elemental form, it's 0. And then in HiO3, the oxidation number of iodine is plus 5. And we can find that hydrogen is plus 1. Let's say iodine is Y. We have 3 oxygens, which are minus 2 each. Overall is 0. Y comes out to plus 5. So the oxidation number of iodine in HiO3 is plus 5. So again, if you think about the disproportionation here, some of the iodine atoms are being reduced from plus 1 to 0. The initial is plus 1, right, and iodine is 0. And some of the iodine atoms are being oxidized from plus 1 to plus 5. Some of the iodine atoms are being oxidized from plus 1 to plus 5. So the change in oxidation numbers for the iodine atoms that are being reduced is minus 1. There's a decrease of 1. And for the ones that are being oxidized, there's a change of plus 4. The oxidation number is increasing by 4, which means that we need 4 iodine atoms. We need 4 iodine atoms to be reduced by minus 1, right? Or for the oxidation number to change by minus 1 for every 1 iodine atom that has an increase in oxidation number of 4, or that has a change of plus 4. So we need 4 of these iodine atoms. We need 4 of these iodine atoms, right, that are a result of reduction for every 1 that are a result of oxidation. So we need 4 of these iodine atoms. That would mean 2I2, right? That's 4 iodine atoms. 2 times 2, that's 4. So 4 of these iodine atoms for every 1 of these iodine atoms. For every 1 of these iodine atoms. The ratio for N is to P is 2 is to 1. So N is 2, and then P is 1. But we've got to make sure that we have a balanced equation with whole numbers, because it could also be 4 is to 2, right? The question is saying we have simple whole numbers in their lowest ratios. So let's make sure that we get a balanced equation with whole numbers. So on the right hand side, we have 2 times 2, that's 4, plus 1, that's 5 iodine atoms. That would be 5 HIO, right? So that's 5 iodine atoms. And then we have 5 hydrogens here. We have 1 hydrogen here. So we're going to need 4 more hydrogen atoms. So that would be 2H2O. So we do indeed get the balanced equation with whole numbers. So N is 2 and P is 1. Sulfur dioxide is added to wines to prevent oxidation of ethanol by air. To determine the amount of SO2, a sample of wine is titrated with iodine. In this reaction, 1 mole of SO2 is oxidized by 1 mole of I2. What is the change in oxidation number of sulfur in this reaction? So the question is saying SO2 is oxidized. SO2 is oxidized by 1 mole of iodine. So that means that as far as the reduction is concerned, right, it's iodine being reduced, right? Iodine atoms will have a decrease in oxidation number because it's the oxidizing agent, right? It's the oxidizing agent. And then sulfur is being oxidized, right? Because sulfur dioxide over here is undergoing oxidation. Now the initial oxidation number of iodine in I2 is 0. The initial oxidation number of sulfur in SO2 is plus 4, right? We have 2 oxygens. You have 2 oxygens, each of which is -2. So that's -4. So that means sulfur must be +4. Now, since the question is saying that we have iodine acting as an oxidizing agent, iodine is acting as an oxidizing agent, that means iodine must be reduced. And when iodine is reduced, it makes iodide. When iodine is reduced, it makes iodide. Okay, that's the only oxidation number of iodine when it has a negative oxidation number. It's -1. Okay, so we have iodine going from 0 to -1. Okay, we have iodine going from 0 to -1. And the question also says that we have 1 mole of I2 reacting. We have 1 mole of I2, 1 mole of I2 reacting with 1 mole of sulfur dioxide. We have 1 mole of I2 reacting with 1 mole of sulfur dioxide. So if you think about iodine and sulfur atoms, we have 2 moles of iodine atoms, right? That's 1 mole of I2 would be 2 moles of iodine atoms for every 1 mole of sulfur atoms. 2 moles of iodine atoms for every 1 mole of sulfur atoms. Now the change in oxidation number for iodine is -1, and we have 2 moles of iodine atoms for every 1 mole of sulfur atoms. Now since iodine has a change in oxidation number of -1, we have 2 moles, the overall decrease is -2, so that one sulfur atom must have a change of +2. Then the final oxidation number of sulfur is +6, so the answer is D. So over here, it's essential to know that the only possible negative oxidation number for iodine is iodide, right? Those are the halide ions. It's a halide ion, right? So knowing that, we know that the change in oxidation number for iodine is -1, and we have 1 mole of iodine molecules for every 1 mole of SO2. That means we have 2 moles of iodine atoms, right, for every 1 mole of sulfur atoms. So we have 2 moles of iodine atoms, each of which, right, each iodine atom has a change of -1. So that'll be 2 times -1. That's -2. So that means that one sulfur atom must be changing by +2, going from +4 to +6.